Complex numbers, section 3.1. Some solutions of quadratic equations include square roots of negative numbers and are referred to as imaginary numbers. Imaginary numbers are useful because some engineering problems have imaginary numbers on intermediate steps. When an imaginary number is added to a real number, the result is a complex number. A set of complex numbers includes real numbers, imaginary numbers, and combinations. Example, use the quadratic formula to find the zeros of f of x equal 1x squared minus 4x plus 5. So a is the coefficient of x squared, which is 1. B is the coefficient of x, which is negative 4. C is the number by itself, which is 5. So we want to plug into the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac over 2a. Replace the letters with the numbers. So minus b becomes minus negative 4. B squared becomes negative 4 quantity squared. 4 times a times c becomes 4 times 1 times 5. 2a becomes 2 times 1. Double negative is positive. So this will be positive 4. Negative 4 times negative 4 is a positive 16. 4 times 1 times 5 is 20. And then and on the bottom, 2 times 1 is 2. Then we can subtract. 16 minus 20 is negative 4. And then we want to simplify that further. We can write, as long as you don't have more than one minus sign under the square root of a product is the product of the square roots. So we can write this as 4 times negative 1, or square root of 4 times square root of negative 1. Square root of 4 is 2. Square root of negative 1 is an imaginary number called I. And then distribute the 2. So it's 4 over 2 plus or minus 2i over 2. 4 divided by 2 is 2. 2 divided by 2 is 1. So we have two solutions, 2 plus 1i or 2 minus 1i. Oftentimes the 1 is not explicitly written. You can write this as 2 plus I or 2 minus I. And terminology, I equals square root of negative 1 is an imaginary number. 2 plus 1i is a complex number. The real part is 2, and the imaginary part is 1. And likewise, 2 minus 1i is a complex number. The real part is 2. The imaginary part is negative 1. Just a comment here. The graph of f of x equal x squared minus 4x plus 5 is, if you write it in the vertex form, x minus 2 quantity squared plus 1, you can see it's a parabola opening up with vertex 2 comma 1. So there's going to be no x-intercepts. There's no way for this to cross the x-axis. And this sort of confirms what we found out before. When we solve for, set this equal to 0 and solve for x, we got no real zeros. We had two complex zeros, but no real zeros. So there's no x-intercepts and no real zeros for this polynomial. Another example, perform the indicated operations with put the answer in the form a plus bi. A plus bi is the standard form for representing complex numbers. So here we have two complex numbers with a plus sign in between. We have 2 plus 3i in parentheses and then added to 5 minus 7i. So what we want to do is add the real parts and imaginary parts separately. So 2 plus 5 is 7. 3 minus 7 is negative 4. So the answer is 7 plus negative 4i, or you could write it as just 7 minus 4i. Technically, the form would, to match this form exactly, you have 7 plus 4i, plus negative 4i, but it's often written as 7 minus 4i. Part B, we have the same expression with a minus sign in between. So now we want to subtract the real parts and subtract the imaginary parts. So 2 minus 5 is negative 3. 3 minus a negative 7 is the same as 3 plus 7, which is 10. So the answer is negative 3 plus 10i. Here we have the same expression with no operation symbol in between. So we could, so it's assumed to be multiplication. And we can use the Floyd method, similar to the FOIL method. F stands for first, so it's the first term times the first term. 2 times 5 is 10. L stands for last, so the last term times the last term. 3i times negative 7i is negative 21i squared, which becomes negative 21 times negative 1. And then the O stands for outer, so the very first times the very last. 2 times negative 7i is negative 14i. And the I stands for inner, the two middle terms. 3i times 5 is 15i. So then we want to combine like terms. I squared is negative 1, so there's negative 21 times negative 1, which is positive 21, plus 10 is 31. And negative 14i plus 15i, it would be positive 1i. So the answer is 31 plus 1i. Or you can just write 31 plus I. Exponents, I to the fourth power, means I times I times I times I. Well, I times I is negative 1, and we have that twice. We have another I times I is negative 1. Negative 1 times negative 1 is 1, or you could write it 1 plus 0i. I to the 67th power. Well, you can write this as I to the 64th times I to the second times I to the first. Any multiple of 4 will have will equal 1. So I to any, here we have I to the fourth, but I to any multiple of 4 is going to be 1. I to the second power is negative 1. I to the first is just I. So you have 1 times negative 1 times I, which is negative I. Or if you want to write it in exactly that form a plus bi, you could write 0 plus negative 1i. 2 plus 3i quantity squared. It means 2 plus 3i times the quantity 2 plus 3i. We can expand this with the Floyd method. First times first, 2 times 2 is 4. The last times last, 3i times 3i is 9i squared, which is 9 times negative 1. The outer, 2 times 3i is 6i. Inner, 3i times 2, which is also 6i. And then combine like terms. 4 plus 9 times negative 1 is negative 5. 6i plus 6i is 12i. So the answer is negative 5 plus 12i. Okay, 2 plus 3i quantity to the third power. Well, we already did to the second power. So we got to write this as 2 plus 3i to the second power times 2 plus 3i to the first. And we know that 2 plus 3i to the second power is negative 5 plus 12i. And then we want to expand this with the Floyd method. So it's first times first, negative 5 times 2 is negative 10. The last times last, 12i times 3i is 36i squared, which is 36 times negative 1. And then the outer, negative 5 times 3i is negative 15i. And the inner, 12i times 2 is 24i. And then combine like terms, negative 10 plus negative 36 is negative 46. Negative 15i plus 24i is 9i. So the answer is negative 46 plus 9i. Okay, here we have a fraction. Fraction bar is like a division bar. So we have 2 plus 3i over 5 minus 7i. It can also be written 2 plus 3i divided by the quantity 5 minus 7i. And what we want to do here is multiply top and bottom by the conjugate of the denominator. The conjugate has the same real part, but the imaginary part has the opposite sign. So the conjugate of the denominator, 5 minus 7i, is going to be 5 plus 7i. And so we want to multiply top and bottom by 5 plus 7i, and then expand with the Floyd method. So 2 times 5 is 10. Last times last, 3i times 7i is 21i squared, which is 21 times negative 1. And then the outer, 2 times 7i is 14i. And the inner, 3i times 5 is 15i. Okay, so 21 times negative 1 is negative 21. 10 minus negative 21 is negative 11. And 14i plus 15i is 29i. On the bottom, I squared is negative 1. So we'll have negative 49 times negative 1. 35i minus 35i is 0. And then negative 49 times negative 1 is 49, plus 25 is 74. So then we want to distribute the denominator. So we'll have negative 11 over 74 plus 29 over 74i. Okay, 2 plus 3i over 2i. Another fraction that can also be written with division. The quantity 2 plus 3i divided by 2i. The conjugate of 2i is negative 2i. This has the same real part, but the imaginary part has the opposite sign. So again, we want to multiply top and bottom by the conjugate of the denominator. And for the numerator, we'll distribute. Negative 2i times 2 is negative 4i. Negative 2i times 3i is negative 6i squared. And the bottom we just multiply. Negative 2 times 2 is negative 4, and we'll have I squared. I squared is negative 1. So I wrote this twice. I squared is negative 1. So we'll have 6 times negative 1 on the top and a 4 times negative 1 on the bottom. 6 times negative 1 is 6. And I wrote the real part first. Usually it's traditional to write the real part first. And then so I have 6 minus 4i over 4. Negative 4 times negative 1 is 4. And then distribute the denominator. 6 over 4 minus 4i over 4. 6 fourths reduces 3 halves. Negative 4i divided by 4 is negative 1i. So the answer is 3 halves plus negative 1i. Okay, so another example, 2 plus square root of negative 3 times the quantity 1 minus square root of negative 3. Now you have to be a little bit careful multiplying square roots of negative numbers, and that's because if there's more than one minus sign, then the rule about the square root of a product equaling the square product of the square roots does not always work. So it's best to get the minus sign outside the square root, and instead rewrite this as, instead of square root of negative 3, write that as square root of 3 times I. So we'll have, we'll rewrite this as 2 plus square root of 3i times the quantity 1 minus square root of 3i. And then we can expand with the Floyd method. First times first, 2 times 1 is 2. Last times last, root 3i times negative root 3i. Root 3 times negative root 3 is negative 3. I times I is negative 1. And then the outer is going to be 2 times negative root 3i. And the inner is going to be 1 times root 3i. Negative 2 root 3i plus 1 root 3i is negative root 3i. Root 3 squared is 3, I squared is negative 1. Negative 1 times negative 3 is 3, 3 plus 2 is 5. So the answer is going to be 5 minus root 3i. Okay, this is the function that we were working with before. We found that one of the zeros was 2 plus I. This is f of x equal x squared minus 4x plus 5. If we evaluate f of 2 plus I, we should get 0, because we found this was supposed to be, we found out before that this was one of the zeros of that function. So let's see if we do in fact get 0. So to evaluate f of 2 plus I, replace x by 2 plus I. So instead of x squared, we'll have 2 plus I quantity squared. Instead of 4 times x, we'll have 4 times the quantity 2 plus I, and copy the plus 5. We can expand this. This is the quantity 2 plus I times the quantity 2 plus I. Distribute the negative 4. This will be negative 8 minus 4i. Copy the plus 5. Expand this with the Floyd method. 2 times 2 is 4. Last times last. I times I is I squared. Outer 2 times I. Inner is 2 times I. I just copied these down. I squared is negative 1. Then we can combine the real parts and the imaginary parts. So we have 4, the real parts are 4 plus negative 1 minus 8 plus 5. 4 minus negative 1 is 3, 3 minus 8 is negative 5, negative 5 plus 5 is 0. And also combine the imaginary parts. We have 2i plus 2i minus 4i. 2 plus 2i plus 2i is 4i, 4i minus 4i is 0i. So we have, we'll have 0 plus 0i, or just 0. So this confirms our previous result that 2 plus I is the 0 of x squared minus 4x plus 5. And that concludes this presentation.